Um, so next, we have our next keynote speakers who will be setting up right now. So James Powell, who is, when I was starting to in my journey in the Python community, being involved with other Python community members, volunteering, speaking, I was impressed seeing James Powell's talk at PyCon Canada many years ago, and where he talked about how to engage with volunteers and how to align goals of volunteers who have personal passions and the bigger goal of the community. And I always found that his talks are super engaging, very unique style. He's a great educator and very entertaining, so I really so exciting to introduce James Powell to you all. Go ahead.
Good morning, everybody. This is I Don't Want to Be a Python Expert. We are at PyCon US number 20 in Salt Lake City. It's Saturday, April 22nd, 2023. I am, of course, James Powell. If you want to follow me on social media, I'm always basically don't use this code. This should also serve as a disclaimer for everything that you're about to see. So, I used to give a lot of really crazy talks about doing things like live patching the Python interpreter to swap out the ceval, pyeval frame X loop. And people would come up to me after the talk and say, hey, I want to be a Python expert too. And my answer to them would be, why bother? What does this really add to your life? And I tried to think a little bit more about this. What does this expertise really add to our lives? Now, I also gave a talk at PyData Seattle in 2017 called So You Want to Be a Python Expert? Because enough people have been asking me about this. What does it take to be a Python expert? And this talk ended up being very popular. Here's something that's quite interesting. I gave the exact same talk 1 week earlier at PyData Berlin, and it was titled Advanced Metaphors in Coding with Python. Almost nobody on YouTube have seen that talk. The clickbait title really works. And if you think about it, it probably makes sense because that word expert is a very loaded term. It means a lot of things to a lot of people, and to an audience like this, for whom we are often valuing ourselves in terms of being thought of as being smart or being thought of as being experts, this term expertise really has a lot of implicit meaning. Oftentimes in my own actual work, I'll see a rejection of this idea of expertise, and it's a very valid rejection. That is to say, I'll work with a scientist or a data scientist or a quantitative modeler who will say, I don't want to be a Python expert. In fact, I don't really even want to be a Python programmer. I just want to be somebody who uses Python to get things done. And I'm extraordinarily sympathetic to that perspective because in the end, what is the value of the expertise itself? The value is what you're able to accomplish with that expertise. And so, let's not talk that much about expertise. In fact, let's start with something very simple. Let's start with something quite elementary in this presentation today. We'll even start with something that you might have covered in your elementary education. Let's start with Newton's method. And for those of you who do not remember what Newton's method is, it is an iterative approach for solving or finding the roots of a real valued function. We often use this to find the roots of a polynomial where there isn't an easy closed form solution like a quadratic formula. And even though we're going to talk about things like Newton's method, what we're going to talk about here is actually broadly relevant to any case where the code that you're writing is a solver, a simulator, an agent model, even things that might look like backtesters, or even things that might look like machine-learned training mechanisms. Well, in Python, making use of something like Newton's method is quite easy. We go into SciPy and we say from SciPy.optimize, import Newton. We give it a function. We optionally give it the derivative of that function, and it'll go and it'll find the roots of this polynomial. And so in this case, it'll find the roots -2 and 4, and it'll tell us that's where that polynomial intersects with the x-axis. Now, this is SciPy, and so NumPy and D-arrays should show up somewhere along the way. Well, in fact, it does. You can provide not just the one guess, not the one initial point, but all of the initial points. So if you bracket those two initial points around the two edges of the parabola, you'll be able to find both of the roots simultaneously. But that's about as far as the use of the NumPy and D-array really gets into this. And so when you think about this, the implementation of SciPy.optimize.Newton probably is very similar to the most naive approach that you might take. It probably looks something like this: a simple for loop where you're looping and then applying that iterative step. And in the case of Newton's method, the iterative step is quite simple. All you're doing is evaluating whatever your guess is, in the function and dividing that by what the derivative is, and then subtracting that until you get close enough to 0. Of course, when you look at this code, you might say, I'm not that happy with it because why do I need 50 iterations? For the polynomial that we just looked at, you don't need 50 iterations to find the roots of that thing. You probably only need 3 or 4. And so we'll parameterize this. And this is, in fact, what the API for scipy.optimize.newton looks like. You have a max iter, and you can give it the maximum number of iterations that you want to run for. But you can think, well, how do I know what the iterations are ahead of time? Maybe I want to give it a tolerance. When you get close enough to 0, then you're done. And if we're going to write this in pure Python, we might make use of the math module, and here we can implement an absolute tolerance. But the moment you see is close abs tol, you think, well, if there's an absolute tolerance, what about a relative tolerance? And the keyword arguments start to grow. Because now we have 3 keyword arguments, max iter, tolerance, and r tolerance, to implement this, and we are now matching very closely to the API of scipy.optimize.newton. Except, if you think about any sort of iterative approach, you might say keep working until there's no additional improvement. Don't keep doing work. Don't burn through my cycles if you're not getting anywhere. And so we might add yet another keyword argument, one which scipy.optimize.newton doesn't have, which just matches from the previous step to the current step, what is the actual improvement here. And we might say if we're going to do the absolute improvement, we should also look at the relative improvement, and this thing is beginning to spiral out of control. Now, there is one saving grace for this, which is we were able to write a function which has a keyword argument titled RIMP for relative improvement, and I don't know about you, but that just feels very SciPy circa 2007 to me, a keyword argument called RIMP. But if you're not convinced that this is beginning to spiral out of control, really think about this. In our first iteration, from the first variation of the function to the second variation of the function, we added a keyword argument to match to what scipy.optimize.newton was doing. And if anywhere in the world, the very last line of code that you see here, where somebody passed in those max iterations as a positional argument, not as a keyword argument, exists, the moment you made this change to this code, you broke their workflow. These people don't want to be Python programmers. They just want to use Python to get things done. They will get on social media and they will abuse you for breaking their code. You did something wrong. And a hard lesson learned, you probably should have used keyword-only arguments to save yourself from this debacle. But there's another hard lesson learned, because if you think about this a little bit, when we look at all the places where somebody might use this code in the wild, somewhere in the wild, one of your users is passing in multiple modalities, both the maximum number of iterations and the tolerance. Is this well defined? What does this do? If you change the underlying code, are you going to break their code? And are you going to get on social media and hurl abuse at you? You don't know. And so it behooves you to either, one, document what happens when all of the interactions of these keyword arguments occurs, which you probably won't do, because if you think about the documentation tooling we have, like NumPy doc, we're very encouraged to document keyword arguments individually and not the interactions of them. That just fits into a block at the very end of the thing. And so very likely you're either going to preclude this entirely, which I don't think is the right choice, because sometimes you want to run for a maximum of iterations or until another criteria is met, or if you really want to be diligent, you need to specify how this works in the form of tests. So you might write a unit test or a property test where you say these are all the different ways this can be called, and I'm going to specify that, and that way, if I make a change to the underlying code, my test will break, and we'll see, not in documentation, but in the form of a test, how to specify the way in which this works. Except the problem here is, for 5 modalities that we have, we need the Cartesian product of either choosing or not choosing that modality, so we need 32 tests. And if we add one additional modality, we need to double the number of tests. This expands geometrically. This will genuinely spiral out of control. And we are obligated to do this because what might appear to be an innocuous change to the way in which this code is written will break user code in practice. If we look at this code and say, if they didn't pass in the imp or the rimp, great keyword argument name if I must say so myself, arguments, we're repeatedly checking in this tight inner loop, whether that's set to none or not. Let's see if we can factor that out of the loop. But the moment you do that, you've broken people's code and you need that unit test in place. And so, note that this has already spiraled out of control, and we haven't really tested the limits of our imagination, because if we can consider all of these ways to do something as simple and elementary as Newton's method, well, somebody can come to us and say, well, could you run this for a fixed amount of time, like a soft real-time limitation? Run Newton's method for 2 seconds and see how far you get? Or maybe we could look at the ratio of adjacent terms, and we could see if those converge to something. A lot of integer sequences converge to particular values. If you think about something like Fibonacci, adjacent terms of the Fibonacci sequence converge to the golden mean. So you could run this until the convergence reaches some particular threshold. Rattal, I don't think is as good as RIMP, but we're still on the right track for 2007-esque SciPy keyword argument names. Having said that, if you really think about this, I've given the game away. The moment I said Fibonacci, half of you out there are thinking this probably should have been a generator from the beginning. And you're right. We should have implemented this Newton's method as just an infinite sequence of steps. And then when somebody says, oh, I want to run this for 50 steps, you say, here's the itertools module, import islice is 50 steps. Or when they say, well, I don't want all of the incremental steps, I just want the end, you say, well, here's the collections module, use collections.dec, and throw away everything except the very last value. When they say, I want this for up until I reach a particular absolute tolerance, that's just itertools.takewhile. If you want this for a relative tolerance, that's just itertools.takewhile with a different lambda. If you want this for some relative improvement or some absolute improvement, that's just takewhile on an n-wise, where an n-wise is a generalization of the idea of getting overlapping windows of some particular size of some data, which is basically just when you take the itertools module and you enumerate t, a bunch of iterables, and then you islice them and put them together. Of course, for those of you who've seen a talk like this before, that's just fan service. You're welcome, Jeff. In fact, these days you just do an itertools.pairwise. But whatever the case may be, we're going to sit in a code review somewhere along the way, and we're going to have to either litigate or adjudicate, is this code actually better than what we started with? We know it's spiraling out of control, but is the other version any better? Well, we already know the answer to this, because all code reviews are all the same. We all know what good code is and what bad code is. Good code is code I wrote, and bad code is code you wrote. But we still have blocked out 30 minutes for the code review session. We probably should take a couple of notes along the way, and let's see if we can litigate this a little bit more deeply. Well, if you think about it, the very first version is just adding keyword arguments. So you do all of the things you want to do with Newton's method in just one line of code. Whereas the second version, you have to have 2 lines of code, and you have to have an import. And if you're a data scientist, you're thinking, you know, why write 2 lines of code when I have to write 1 line of code? I'm very sympathetic to that attitude, but definitely data scientists, you know who you are. Additionally, in order to even understand how all of this works, you need to know what a generator is. You need to know what the itertools module is. A set of colleagues of mine have created a framework for data acquisition and data management around X-ray beamlines. And the dominating concept for that framework is PEP 380 delegation to a sub-generator. If you think a scientist will complain when you show them a generator and yield, see what happens when you show them yield from. There's a bar that you have to meet to be able to use this code. And the question might be, is it worthwhile for us to inflict those requirements upon our users? But on the other side, you might be able to mitigate a little bit of that by creating a convenience layer. So the core layer looks one way using all of these advanced functionalities, and there's a convenience layer. And when we look at a lot of projects in the PyData ecosystem, you see this pattern of the core and the convenience layer. Matplotlib and PyPlot are very good examples of that. And maybe that allows you to write tests a little bit better. The convenience test can be a little bit more superficial, and the core test can be a little bit more exhaustive. So there might be some benefit there. But I think one thing that hasn't come up at all in our code review is the design of this, or specifically, the absence of design. That is to say, if we are to clumsily define the word design in a way that we don't typically define it, to be any decisions that we make to address questions whose answers are unknowable or unverifiable. Anything that we make which we say, this is a judgment call, I think this is how this is going to be used, I think this is what our users want, I think this is what people want to do with this. Well, there's a lot of these calls, and there's no right or wrong answer. Even if you think about the temporal dimension, it may be the case that the right answer today is the wrong answer tomorrow. Design is not necessarily timeless. It's oftentimes very idiosyncratic or very specified to a particular period of time. Well, of course that makes sense, because if we think about design, we're thinking about, especially when we talk about APIs, the accommodation to the human requirements. How does a human being going to use this? And this necessarily means accommodation to the infinite profundity of the human experience. So design doesn't really have a right or a wrong answer. It's just what seems to work and what you can get away with. And you're always trapped in this puzzle of, well, did I get it right? Did I get it wrong? Do I know if I got it right? Do I know if I got it wrong? Well, if we're willing to accept the clumsy definition of design, maybe we're willing to accept a clumsy dichotomy between the idea of design and effort, where if design is trying to approach these unknowable questions, effort might be the processes that we take to do things to solve problems that are knowable and that are verifiable, where we just know it's just a matter of number of lines of code that we have to write. And so, if we think about this, the core convenience layer dichotomy, I actually don't like that very much, because you're just trading the design at one level for the design at another level. You're still making a decision for what somebody wants to have available to them, what they want to see, what modalities they care about, what modalities they don't care about, and you've narrowed the problem only very slightly. In fact, I actually think the preferred solution here is to make the scientists use generators, and to teach them generators, and to teach them about the itertools module, and to avoid the design problem entirely. Don't presume that you know the modalities that they care about. Just give them a generator and let them supply whatever they want to do. But this does necessarily introduce some complexity, and we can take this complexity to the extreme, because honestly, I have written this in real code before. Some of you are looking at this, you have no idea what this is all about. I am a very strong believer in the idea of pre-pumped generator coroutines. I have to remind you one more time, don't use this code, folks. But if we think about this dichotomy that we've set up, clumsy as it is, between design and effort, we can think that what makes us better at design is judgment, and what makes us better at effort is expertise. That is to say, by understanding these complex mechanisms that we have, we can lever our expertise to turn problems that have an unknowable aspect to them into problems that have a knowable aspect to them. And to be honest, I am very skeptical about my own judgment. After all, look at how I'm dressed. But I'm much more confident about my ability to leverage expertise, because largely the expertise that we're talking about here, the expertise of using parts of Python that are considered to be more advanced or considered to be more esoteric, it's largely about a conceptual expertise that can be very obvious, in fact, and can be methodically constructed, and most importantly, can be methodically instructed. I'll give you an example. We talk about generator coroutines, and we put this in front of a scientist, and they have no idea what you're talking about. They've never seen this before. Their familiarity is with mechanisms that they've learned when they first learned programming using MATLAB or C or maybe even C++. But you can share with them a very simple idea. We can represent data in multiple different ways. We can represent the exact same data, the three entities, A, B, and C, as a string or as a list. But beyond the superficialities, whether it's a list or a string, we can see that there's something a little bit deeper here. In other words, one of these is an in-band encoding, and the other is an out-of-band encoding. One of these uses a single channel for representing the metadata and the data, or the structuring, and the other one uses distinct channels. The string conflates the commas which are delineating the data with the actual values themselves, and the list has an out-of-band encoding where there's no way for you to mistake, is this a comma that's part of the data or not? And we know in-band encodings are fundamentally ambiguous. And so we run into these problems where, is this A, B, C, D 4 entities, or A, B, C, comma, D, where the comma is part of the entity, 3 entities? The out-of-band encodings are fundamentally unambiguous. Well, in a very similar sense, we can think, when we want to disambiguate these in-band encodings, we have a set of techniques, and the techniques are almost always the same: partitioning, quoting, escaping. When you think about partitioning, you think about taking the input data space and designating certain input values as being only metadata. So an example of that would be the bit patterns that are NANDs and payload NANDs and IEEE 754 double precision floating point. You have quoting or escaping. Of course, CSV is very famous for this. You have mechanisms like prefixing, which don't show up that much in our programmatic mechanisms, but if you look at how get objects are represented, there's a prefixing mechanism where it says the next number of bytes are the underlying payload itself, and you see these in network protocols. And when you think about some of the things that we as data scientists have to deal with in contemporary versions of tools like pandas, things like the D type with a capital I in 64, well, this is actually an out-of-band encoding very similar to the NumPy masked array to represent missing values in the absence of an unambiguous partitioning of integer data. Largely, despite all of the verbiage behind this, many of these things are quite obvious. And oftentimes when you see these core concepts, which are very easy to point out to somebody, you can't unsee them. I'll give you an example. Some of you out there are users of a very, very high quality, very nice package called Xarray that combines the ideas of NumPy and pandas together. And for those of you who aren't that familiar with Xarray, I'll give you a very brief refresher. NumPy is all about representing multidimensional data with broadcasting. Pandas is all about representing index-aligned one-dimensional data. And Xarray is about doing coordinate-aligned multidimensional data. I must, and I am obligated for a very brief aside. Number one, the pandas data frame is not two-dimensional. The pandas documentation says it is. The pandas documentation is wrong. Pandas data frames are like indexed one-dimensional data. You heard it here. I will take that to my grave. Number two, for those of you who are complaining about pandas, Gilad, I know you're out there, The API of pandas is guaranteed. It is absolutely very inconsistent. It's sometimes swap underscore levels or drop level with no underscore. It's very inconsistent, but the core concept behind the tool is incredibly coherent. And 3, the only thing you ever really have to know to be really good at pandas is index alignment. They once asked me to write a book on pandas. They asked me for the chapter outline, and I said chapter 1, index alignment, chapter 2, everything else, and then the epilogue. There's only index alignment and nothing else. That's the only interesting thing about pandas and the only thing you have to know. But back to X-ray. When we talk about X-ray, we're representing multidimensional data with some dimension. So you have maybe a volumetric data, and you have an X, a Y, and a Z dimension. And you can select a slice of this down the X-axis or down the Y-axis or a combination of these. You can even interpolate this if you have missing values. And because this is a wrapper on top of tools like NumPy, Pandas, and SciPy, you can even pass an interpolation method. You can use SciPy interpolation methods, linear or cubic or whatnot, in order to choose how that interpolation works. But what if your dimension is called method? This is fundamentally ambiguous because it's an in-band encoding where you're conflating the single channel, the keyword arguments you have, to either represent 1, the modality of how you do the interpolation, or 2, the data that you're interpolating on. There is no resolution for this. This is a flaw in the API, and it's as obvious as you cannot unsee it once you see it. And the solutions are largely quite routine. You want to find an unambiguous encoding, partitioning, quoting, prefixing, none of those will work in this approach. So what you'll do is you use an out-of-band encoding, like you'll have 2 layers of a function, but nobody likes that. Or you'll do something like pandas.lock and .ilock, where you'll create one more layer using the descriptor protocol or using some other protocols in Python. And so you might do something like this to say this is the linear interpolation for these particular axes. Or you might realize that this is just the problem of a nominal decomposition of a bounded modality. In other words, there's only a set number of possible interpolations that you have. SciPy only supports less than a dozen of these. You can put a name on each of those. This is basically the idea behind class method that we do all the time. You could just have a bunch of methods, linear underscore interp, and you would have solved this problem entirely. Now, once you see the problem, you can't unsee it. And I'm certain that you're going to begin to see these problems in the actual code that you have. When you think about this difference between the in-band encoding and the out-of-band encoding, well, that's basically what a generator is all about. The core concepts here are actually quite simple and quite present there. They're obvious and they're in front of you and they can be methodically thought through. Because if we have some function that does a bunch of different things, we might, as a human being, put step numbering on these. A function that loads some data, cleans some data, removes outliers, and processes some data contains 3 steps. Step 1, step 2a, step 2b, step 3, or maybe 4 steps corresponding to the lines of code that we have. But in truth, this is an ambiguous in-band encoding for the structuring of the underlying computation. And all a generator is an unambiguous out-of-band encoding for the structuring of a computation. It unambiguously delineates, this is where the first step is, this is where the second step is, this is where the third step is, and this is where the fourth step is. And the moment you have an out-of-band encoding for the structuring of this function, you can do things like unambiguously delineate the steps, which means you can then create mechanisms for controlling how many steps you run through, which is the core problem that we had when we were using our various implementations of scipy.optimize.newton. We were constantly having to add additional keyword arguments to control the number of steps of the iterative method that we go through. Well, we can devolve that entirely with just a very simple conceptual idea. We can devolve those modalities such that instead of presuming that we know we're going to run for a maximum number of iterations or into a relative tolerance or an absolute tolerance, we just say we'll run forever, but we'll structure the computation so that you can choose how you want to do this. And we can empower the end users to do things which are not capable with the scipy.optimize.newton implementation that we have today, which of course I don't want to criticize too much because there's a lot of historical baggage to these tools and many reasons why they're written the way they are. But we can devolve those modalities to allow things like complex combinations of these stopping conditions that are otherwise impossible to easily represent in the form of just keyword arguments. From this perspective, we can actually come to an answer for why bother with the expertise in the first place. If we reframe the idea of expertise as the methodical approach to devolving design into effort, to taking questions which cannot be answered because they are fundamentally a consequence of adapting to some human requirement, where we have to make assumptions about, well, are they going to use it this way? Are they going to use it that way? Are they going to want to do this? Are they going to want to do that? And we discover through the advanced mechanisms that are available in a programming language like Python, mechanisms like generators or context managers or metaclasses, or even some of the more esoteric mechanisms that are available when you start digging deeper, like import hooks and whatnot, we can oftentimes devolve that design into effort. And we can remove the unknowable quantity of design. We can then just implement some mechanism that allows us to not have to guess, are we going to get this right or wrong, and not have to risk spiraling into this unknowable, uncontrollable future. Because if you really ask me, I don't want to be a Python expert. I don't even want to be a Python programmer. I don't even want to be a programmer at all. I do want to be somebody who uses programming to get something done, but the answer of expertise and the motivation for this is really, can I be more effective in the work that I do via a deliberate, methodical approach to developing expertise? And I think I've made a compelling case for why that may be. This has been I Don't Want to Be a Python Expert. I'm James Powell. Thank you all.